If you've been seeing posts screaming that the James Webb Space Telescope just captured the first real image of 3I/Atlas and that it doesn't look natural, slow down. Subscribe right now, because we're gonna do something most people refuse to do online. We're gonna check the claim like grown-ups. Because the internet has a habit. The moment something looks weird, people jump straight to it's artificial or it's a cover-up. But here's the honest rule of space reporting. If a claim is huge, the proof has to be boring. And right now, the boring proof is the whole story. So here's the open question we're answering today. Not, is it aliens? The real question is this. Why does 3I/Atlas look wrong in some images? And what would it take to prove it's actually doing something impossible? Because even if this ends up being a normal interstellar comet, this is still a once-in-a-lifetime kind of moment. An object from outside our solar system passes through, and suddenly our telescopes, our software, and our own brains are under stress because we're trying to understand something we barely have a category for. So let's start with the part that matters. James Webb is not a casual camera. Webb is a machine built to see faint heat signatures, gases, dust chemistry, and structure the kind of details that tell you whether an object is a dirty snowball or something else entirely. The telescope is operated with extreme procedures. Not because NASA is dramatic, because space telescopes don't get second chances. And when Webb looks at something moving fast, like an interstellar object, it's not like pointing a phone camera at a bird. It takes planning, tracking, calibration, background, subtraction, correcting noise, removing cosmic ray hits, comparing frames. All of that is where the monster stories are born. Because if you don't understand how images are processed, you can mistake a processing artifact for a structure. You can mistake a saturated pixel for a glowing beam. You can mistake a dust tail for a sun-facing tail that breaks physics. And yes, you can mistake a natural thing doing natural things for an engineered thing doing engineered things. So I want you to picture this like a courtroom. The internet is yelling, guilty. It's artificial. But NASA-style reporting says, hold on, show the evidence, then show the chain of custody. That's why this gets scary, not because of aliens. It gets scary because it shows how easily people can be pushed into certainty with one weird image and a confident voice. Now, what do we actually know in the solid, boring, checkable world? We know 3I/Atlas is classified as an interstellar object. That 3I means it's the third confirmed one we've tracked through the solar system after 1I/Oumuamua and 2I/Borisov. Interstellar means it's not looping around the sun like normal comets. It's passing through on a hyperbolic path, like a rock thrown through a room. We also know that the moment something like this shows up, the whole astronomy world lights up. NASA teams, the Jet Propulsion Laboratory orbit folks, the Minor Planet Center, university observatories, the European Southern Observatory networks, the big scopes like Keck in Hawaii, the Very Large Telescope, the Gemini telescopes, everybody tries to get time on it because interstellar objects are rare and the first days of data matter most. Now here's where the it's impossible claims usually start. People say it has a tail going toward the sun day. Let's talk about that because that sounds like a law of physics got broken. Comets usually have two tails, a dust tail and an ion tail. The ion tail generally points away from the sun because the solar wind pushes it. The dust tail curves and lags behind because dust is heavier, and it follows the comet's orbit more than the wind. But there's also something called an anti-tail, and it's not magic. It can look like it points toward the sun because of geometry, the angle we're seeing it from, and the way dust spreads in the plane of the comet's orbit. So yes, a sun-facing tail can be a real-looking illusion that happens without breaking physics. That's reason number one. We don't scream contact. Nature plus perspective can produce something that looks like a sign. Now, people also claim it shot a concentrated beam. Again, careful. A beam in an image can be a lot of things. It can be a jet of gas and dust coming off one active region. It can be motion blur if the tracking solution isn't perfect. It can be image saturation if the object is bright against a dark background and the detector clips the highlight. It can be a cosmic ray hit that leaves a streak on the detector, or it can be a processing artifact where the algorithm tries to remove background stars and accidentally leaves behind a sharp feature. That last one is a big deal because when you're tracking a moving target, you often subtract the background stars. If your subtraction isn't perfect, you can create shapes that look crisp and artificial. So the first question is not, did it emit a beam? The first question is, do we see the same feature across multiple instruments and multiple telescopes? Because if the beam only appears in one process frame and not in raw stacks, it's probably not a beam in space. It's a beam in software. Now, your summary mentions a leaked Webb image. Here's how a NASA reporter handles that. We treat leaked the same way we treat my cousin said. It might be true. It might be fake. It might be real data edited by someone who doesn't understand the processing. So we don't build a conclusion on the word leaked. We build a conclusion on repeatability. If it's real, it will show up in independent data sets. Now, people also claim it has perfect symmetry. Okay, let's be honest. Symmetry is a trap. Snowflakes are symmetric. Crystals are symmetric. Honeycomb is symmetric. Saturn's hexagon is symmetric. Jupiter's storms can lock into stable bands and repeating patterns. Nature doesn't avoid geometry. Nature loves geometry. So when someone says it's symmetric, so it's artificial, that's a weak argument. The stronger argument would be this. Is the symmetry stable over time in a way natural objects can't maintain? Because comets are messy. Jets change. Dust changes. Rotations change. The coma changes. If a pattern stays perfectly stable through rotation and changing sunlight, that would be weird. But even then, you still have to rule out the camera and software. Now, let's get to the part you asked about directly. You asked, am I trying to let listeners know it was done by AI? Yes, but in a specific way. AI can reanalyze archived telescope frames and pull faint patterns out of noise. That's real and common. Universities do it. Space agencies do it. Even amateur astronomers do it with stacking software. AI can also hallucinate patterns, not because it's evil, but because pattern-finding systems hate randomness. If you tell a system find structure, it will find structure. So if someone online says, AI found a hidden image, the NASA response is, show the raw frames, show the calibration steps, show the instrument artifacts, show the statistical confidence. Because without that, AI found it is not proof. It's a headline. Now, your summary also talks about RNA-like repeating sequences and fractal geometry like the human brain. That's where we put on the brakes because there's a difference between a pattern and a biological code. To claim RNA-like sequences in a space signal, you'd need very specific analysis and you'd need multiple teams to reproduce it. And the looks like a brain thing is dangerous. Not because it's scary, because human brains are built to see familiar shapes in everything. That's why people see faces in clouds. So in this video, if we include those ideas at all, we treat them as speculation that needs heavy proof, not as a revealed truth. Now, let's talk about the trajectory claim. The summary says the object follows a gravity assist path like human spacecraft routes. This is another one where truth and misunderstanding can look the same from far away. Objects passing through the solar system can appear to thread near planets simply because of where the planets are. Gravity assist is just gravity. It's not a secret technology. If something passes near Jupiter, Jupiter can bend its path. That doesn't mean it planned it. It means Jupiter is huge and rude and doesn't ask permission. But here's what would be genuinely weird. If the object changes course in a way gravity can't explain, if it accelerates without outgassing, that matches the acceleration. If it performs timed changes that line up with a rotation period, like a controlled thruster, those are measurable. And this is where we bring in real science names naturally, because this is how real science is done. When weird interstellar behavior showed up with Oumuamua, it sparked serious debate, not because everyone became alien hunters, but because the acceleration didn't neatly fit expectations. Harvard astronomers like Avi Loeb argued for artificial possibilities. Many others argued for natural explanations, like outgassing, unusual shape. or other mechanisms. That's how science works. Competing models. Data decides. For 3I/Atlas, the strongest credible approach is the same. You watch the light curve, you watch the spectrum. You watch the gas emissions, carbon monoxide, carbon dioxide, water vapor, signals the kind of chemistry Webb can detect using instruments designed for faint infrared fingerprints. You compare it with what Hubble sees, invisible light. You compare it with ground-based spectroscopy from places like Keck and ESO facilities. You check whether the jets match the thermal model, and you use JPL-style orbit fitting to see if the motion requires non-gravitational forces. Non-gravitational forces is a boring phrase that causes internet chaos. It usually means outgassing. Gas leaving the comet acts like a tiny rocket. So if 3I/Atlas is outgassing, it can accelerate slightly. That's normal. What's not normal is when the acceleration doesn't match the observed gas production. That's when the mystery becomes real. Now, the summary says it disappeared behind the sun at peak activity and evaded observation. This part is actually relatable because it happens all the time. When something gets too close to the sun in the sky, it becomes hard to observe from Earth. Solar glare, geometry, safety constraints for telescopes. That's not proof of stealth. That's proof the sun is a giant flashlight pointed at your eyes. So we acknowledge that. We use it as tension, but we don't use it as evidence of intention. Then there's the silence by agencies claim. This is where a NASA reporter has to be honest. Space agencies don't usually go silent because they're hiding aliens. They go quiet because they don't want to publish half-baked results. They don't want people to misunderstand preliminary data. And sometimes because observations are proprietary for a while. Also, US Space Command and UN offices get thrown into stories because those names sound powerful. But powerful names are not proof. Proof is data that multiple independent teams can test. So here's the tone we set for the audience. We're not here to scream. We're here to watch something that might be rare, might be strange, and might force scientists to update their models. That's already exciting enough. Now, let's rebuild the core mystery in a way that's scary for the right reason. Not what if it's a probe, but what if it's natural and our models are still too small? Because if 3I/Atlas shows behavior we can't explain with the physics we're confident in, that doesn't mean aliens. It means interstellar space can produce objects that don't behave like the stuff we grew up observing in our own solar neighborhood. It means our sample size is tiny. 3 objects is not a population, it's a hint. And here's a haunting thought that doesn't require any conspiracy. If interstellar objects pass through more often than we detect, then we've been missing most of them. Not because someone is hiding them, because the sky is huge, and these things are small, and they move fast. That's why the Vera Rubin Observatory matters so much. Wide field surveys catch motion. Motion reveals visitors. And if Rubin-era surveys start catching interstellar objects regularly, then the scary part is not contact. The scary part is realizing we've been living beside a cosmic highway and only just started noticing the traffic. Now let me give you the clean investigative frame you wanted, because it keeps viewers grounded while still hooked. Step 1. Confirm the image is real by cross-checking with official observation logs and independent observatories. Step 2. Confirm the impossible features exist in raw data, not just processed images. Step 3. Confirm the motion fits gravity and outgassing. Step 4. If it doesn't, then you build theories, not before. And while we wait, we can still explore what Webb is actually good at. Webb doesn't just take pretty pictures. It can detect what the object is made of by looking at how it absorbs and emits infrared light. That's where the truth tends to hide, because you can fake a picture on the internet, but you can't easily fake consistent spectral fingerprints across instruments. So if 3I/Atlas is rich in certain ices, certain gases, certain organics, Webb will see that. If it's unusually low in water compared to what we expect, that's data. If it's producing unusual compounds, that's data. If it's emitting atomic metals like nickel in odd ratios, that's data. And those are the kinds of boring details that build a real mystery, not it looked like a triangle. Now, I want to tell you the real emotional center of this story. It's not aliens. It's trust. The audience has been trained to either believe everything instantly or reject everything instantly. But the only way we get through a moment like this is patience. Let the scientists do the slow work. Let the data accumulate. And keep your curiosity alive without letting your fear drive the steering wheel. Because if 3I/Atlas turns out to be natural, it's still one of the most important visitors we've ever studied. And if it turns out to be not natural, then the story changes forever. But either way, the only path that earns the truth is the boring one. And that's the path we're walking. So here's the question that should sit in your mind as we go deeper. What would it look like in real data if an object was truly engineered? Not in a blurry image, in numbers, in repeatable behavior, in physics that refuses to fit. Because if we can define that clearly, then we can finally stop arguing like a comment section and start thinking like a species that actually wants to survive in a big universe. Now, the next thing we need to do is zoom in on the specific impossible claims one by one and test them against the three biggest imposters: spacecraft quirks, processing artifacts, and nature's geometry. And when we do that, some of the claims will collapse immediately. And the ones that don't collapse, those are the ones worth losing sleep over. What actually matters with 3I/Atlas is not how strange it looks in one frame, but whether its behavior survives contact with math. The first thing teams do is strip away everything that can lie to you. Telescopes lie. Software lies. Perspective lies. So you start with motion, because motion is the hardest thing to fake. When JPL analysts run in orbit, they don't eyeball it. They feed in time-stamped positions from multiple observatories taken at different wavelengths, corrected for Earth's motion, corrected for light time delay, corrected for instrument bias. The output is not a picture. It's a cloud of probabilities that shrinks as more data comes in. With 3I/Atlas, that cloud tightens the way you expect an interstellar object to tighten. Hyperbolic path, high inbound velocity, no bound orbit. So far, boring in the best way. Then comes the uncomfortable part. You subtract pure gravity. What's left is the residual. The tiny mismatch between where gravity alone says the object should be and where it actually is. For most comets, that residual screams outgassing. You see jets, you see water, carbon monoxide, carbon dioxide. You see the thrust line up with sunlight. The math behaves. With 3I/Atlas, the residual is small, but it's stubborn. It doesn't vanish cleanly unless you assume very specific jet behavior. Not impossible behavior, just narrow. That's the difference between this breaks physics and this stresses our assumptions. Now you bring in chemistry, because chemistry doesn't care about internet arguments. James Webb looks for fingerprints. Not shapes, not silhouettes, fingerprints. Certain gases absorb certain wavelengths. Certain ices glow in infrared when heated. Certain metals show up only if you're seeing exposed material rather than fluffy dust. What Webb reports, when it reports anything at all, is not structure, it's ratios. And ratios are where this gets interesting. The gas profile does not look like a textbook long-period comet from our own solar system. That does not mean artificial. It means foreign. Interstellar is not just a travel label. It's a manufacturing label. Different star systems cook their debris differently. If you grew up around only one bakery and suddenly tasted bread from another country, you wouldn't call it fake. You'd call it unfamiliar. That's where a lot of claims die quietly. The so-called beam reduces to a narrow jet when you account for viewing angle and rotation. The sun-facing tail becomes a geometry trick when you rotate the dust plane in 3 dimensions. The symmetry breaks once you stack frames across different rotation phases. Not all at once, but enough. Then there's the part people really don't like hearing. Interstellar objects don't owe us intuitive behavior. We learn comet physics by studying local junk, stuff that formed in roughly the same disk, under roughly the same radiation, with roughly the same chemistry. That makes our models neat and comfortable. 3I/Atlas didn't grow up here. So when it vents differently, rotates oddly, or sheds dust in ways we haven't cataloged yet, the correct response isn't fear, It's humility. Now let's talk about the trajectory, because that's where the word engineered keeps getting smuggled in. Yes, the path brushes regions where gravity assists are possible. So does almost everything that passes near a giant planet. Jupiter bends paths like a bully bends hallways. You don't need intent, you need mass. What would matter is timing. A gravity assist only looks clever if the object arrives at a precise window. Miss the window, and nothing dramatic happens. Right now, 3I/Atlas is early. Too early to claim precision. The uncertainties are still larger than the cleverness people are projecting onto it. That may change as more data comes in. Or it may collapse into noise. Either outcome is fine. Here's the part that actually deserves your attention. If this object shows repeated phase-locked behavior, meaning the same jet activates at the same rotational angle regardless of solar distance, that would force model updates. Not alien updates, physics updates. If the non-gravitational acceleration stays constant while gas output drops, that would be weird. Still not proof of machinery, but weird enough to demand new mechanisms. That's where real discoveries come from. Not from leaks, not from silhouettes, from numbers that refuse to behave. And this is where the story quietly widens beyond 3I/Atlas. Because if this object turns out to be natural but unfamiliar, it means our definition of normal is local and outdated. It means the galaxy is throwing debris at us that we've never trained our intuition on. That's unsettling in a grown-up way. It means the universe is not required to feel familiar just because we've been naming things for a few centuries. So here's the honest state of play. No confirmed image shows a machine. No verified data shows propulsion without mass loss. No instrument has detected encoded communication. No agency has issued a classified warning disguised as silence. What we do have is an interstellar visitor that behaves differently enough to make careful people lean forward. That's it. And that alone is enough to keep watching. Because the scariest stories in science are not the ones where the answer is obvious. They're the ones where the answer keeps slipping just out of reach. Not because someone is hiding it, but because reality is more complex than our categories. So the question is no longer, what is it? The real question is whether we're ready to accept answers that don't flatter our expectations. Because if the universe is about to teach us something new, it won't announce itself with drama. It will do it with data that refuses to sit still. And right now, that data is still coming in. And this is where the tension settles into something quieter, but heavier. Because once the obvious explanations are tested and the loud claims fall away, you're left with a smaller set of questions that don't go away so easily. The first one is rotation. Every solid object in space spins. Comets spin. Asteroids spin. Even irregular chunks spin. And the way something spins controls everything else. Where heat builds up, where cracks open, where gas escapes. So astronomers start tracking the light curve, not because it's flashy, but because brightness rising and falling tells you how fast something rotates and how uneven its surface is. With 3I/Atlas, the light curve isn't chaotic, it's structured. Not perfectly clean, but consistent enough to suggest a stable rotation state. That alone doesn't mean anything artificial. Plenty of natural bodies settle into stable spins. What matters is whether the activity lines up with that spin. When jets turn on and off at the same rotational phase, again and again, you can map where the active regions are. That's normal comet science. It's been done since long before computers could draw pretty simulations. But when the active regions appear unusually narrow, unusually persistent, or oddly placed compared to what we expect from a loosely bound icy body, that's when people stop chatting and start recalculating. Not panicking, recalculating, because narrow jets can come from fractures. Fractures can come from thermal stress. Thermal stress can come from repeated heating and cooling over millions or billions of years in interstellar space. That's still nature, but it's a kind of nature we've barely sampled. Now bring in the tail. Again, not as a shape, but as a mass problem. Dust tails spread because dust particles have different sizes and different responses to sunlight and solar wind. If the tail stays unusually tight, unusually columnated, that tells you the dust size distribution is skewed. Either the object is shedding very similar sized particles, or the dust is being released in a very controlled way by the surface geometry. Again, neither option breaks physics. Both options say, this thing is not built like the comets we're used to. That's the honest discomfort. Then there's the timing. 3, I/Atlas doesn't exist in isolation. It's moving through a solar system that is itself dynamic. The sun isn't constant. The solar wind isn't constant. Magnetic fields twist and reconnect. Charged particles stream and thin. That's why data from missions like Parker Solar Probe and Solar Orbiter matter here. Even though they're not looking at the object directly, they tell us what environment the object is flying through. If solar wind conditions line up with unusual tail behavior, the mystery shrinks. If they don't, the mystery deepens. This is how real investigations feel. Not like a reveal, like pressure. And then there's the part people really underestimate: statistics. Interstellar objects are rare to us, but not necessarily rare in the galaxy. The reason we've only seen a few is not because they're uncommon, but because they're hard to catch. Small, dark, fast-moving things don't announce themselves. So when people say, why now? The answer may simply be, because we finally built eyes good enough to see them. The Vera-Rubin Observatory is going to change the story completely. Wide field surveys that repeatedly scan the sky will start catching these visitors earlier, farther out, with better context. When that happens, today's arguments will look primitive. We'll stop asking whether one object is strange and start asking how many varieties exist. And that's when the emotional center of this story shifts again. Because if 3I/Atlas is one of many, then it's not a message, it's a sample. A single pebble from a beach we've never walked on. And pebbles from other beaches don't have to look like ours. They don't have to behave like ours. They just have to obey physics we haven't fully mapped yet. Now, none of this erases the unsettling parts. It just puts them in their proper place. If future observations show that the non-gravitational acceleration doesn't match any plausible gas production, that's a problem. If jets appear without corresponding spectral lines, that's a problem. If the object changes trajectory in ways gravity and outgassing can't explain, that's a serious problem. Those are the thresholds. Not vibes, not symmetry, not silence, numbers. And here's the thing most people don't realize. If any of those thresholds are crossed, the response won't be secrecy. It will be chaos, papers, preprints, competing models, public debates between serious scientists who disagree loudly, but professionally. That's how anomalies die or become discoveries. Silence is boring. Science is noisy. So the absence of fireworks right now doesn't weaken the story. It strengthens it because it tells us the data is still being digested, not weaponized. And while that digestion happens, 3I/Atlas keeps moving quietly, indifferently. It doesn't care about our fear or excitement. It doesn't care about headlines. It's just doing whatever its structure, composition, and history force it to do. And that might be the most unsettling thought of all. That something can pass through our system, bend our assumptions, and leave again without ever needing to acknowledge us. Not because it's intelligent, but because the universe doesn't revolve around curiosity. It revolves around laws. And right now, we're watching to see whether those laws hold exactly as we expect or whether they need to stretch. And that question, stretch or break, is where this story is actually heading. There's another layer to this that almost never gets discussed because it's uncomfortable for both skeptics and believers. Intent is the hardest thing to prove in the universe. Physics can tell you how fast something moves. Chemistry can tell you what it's made of. Geometry can tell you how it's shaped, but intent lives in patterns over time. And right now, the only thing we truly have is one pass, one fly-through, one narrow window where an interstellar object briefly intersects our backyard and then keeps going. That's not a conversation. That's a drive-by. So scientists look for something else instead. Consistency across independent systems. If an object shows unusual motion in imaging data, you check radio data. If the radio data looks odd, you check plasma measurements. If plasma data looks structured, you check whether the sun, the solar wind, or the local magnetic field could explain it. This is why progress feels slow. Every explanation has to survive multiple attacks. And sometimes Explanations survive not because they're exciting, but because they refuse to die. Take non-gravitational acceleration again. This has been the center of past debates for a reason. Outgassing doesn't have to be dramatic to be effective. Hydrogen, for example, can escape without leaving obvious spectral fingerprints. Ice structures can trap and release gases in ways that look nothing like classic comets. That doesn't mean the models are perfect. It means they're stubborn. Now, zoom out even further. Our entire classification system for small bodies is built on solar system residents. Things that formed in roughly the same disk, from roughly the same materials, under roughly the same conditions. Interstellar objects are immigrants. They formed around other stars with different radiation histories, different chemistry, different collision timelines. Some may be older than our sun itself. So when one of them looks wrong, the honest response isn't fear, it's humility. We're comparing something foreign to a rule book written for locals. And here's where the story becomes quietly profound. Because even if 3I/Atlas turns out to be completely natural, no technology, no intelligence, no signal, it still tells us something unsettling. It tells us the galaxy is full of things that don't care how comfortable our categories are. It tells us that our sense of normal is provincial. That realization alone reshapes how we think about risk, rarity, and discovery. Now, about alignment. Planetary alignments feel powerful because they're visually simple. Lines, angles, symmetry. Humans are wired to see meaning in those. But alignments happen all the time in three-dimensional space. What matters isn't whether bodies line up, but whether the forces involved meaningfully interact. Gravity falls off with distance. Magnetic effects depend on fields and plasma. Tidal forces require proximity. Most alignments look dramatic on diagrams and do nothing physically. So when simulations show an object passing through a visually striking configuration, scientists ask a dull question. Does anything measurable change? If the answer is no, the alignment is cosmetic. If the answer is yes, then you dig. And so far, nothing in the numbers screams disruption. No sudden orbital kicks. No unexplained accelerations. No energy transfers that don't add up. That doesn't mean nothing is happening. It means nothing is breaking. And that's an important distinction, because the universe is allowed to be strange without being threatening. Now let's address the emotional core of why this story grips people. It's not really about aliens. It's about surprise. For centuries, the sky was predictable. Cycles, seasons, motions you could set your life by. Then technology arrived, and suddenly the universe started throwing curveballs. Pulsars, quasars, dark matter, dark energy. Things that didn't fit intuition. Interstellar visitors belong to that tradition. They remind us that the solar system is not sealed, that the galaxy is not quiet. That stuff moves between stars all the time, and most of it passes unnoticed. So when one of those travelers finally gets noticed, it feels personal. Like someone walked past your house at night and you caught a glimpse, not because they were watching you, but because you finally turned on the porch light. That's where we are right now. Watching, measuring, waiting for the data to either settle the nerves or sharpen them. And here's the part that matters most going forward. The next interstellar object will be more important than this one. Not because it'll be scarier, but because patterns require repetition. 2 data points are interesting. 3, start a trend. 10, rewrite textbooks. We are at the beginning of that curve. So whether 3I/Atlas becomes a footnote or a milestone doesn't depend on fear or hope. It depends on what comes next. And somewhere out there, long before we ever noticed, whatever made this object was already gone, or still coming, or completely indifferent. And that indifference, the idea that the universe doesn't react to our curiosity, is what gives this moment its weight. Because we are no longer asking, is something out there? We are asking, how much of what's out there have we never learned how to recognize? And that question doesn't end when this object leaves the frame. It follows us into every future discovery we haven't made yet. There's one more uncomfortable truth hiding underneath all of this. Most discoveries don't announce themselves when they happen. They announce themselves years later. Voyager didn't feel historic in real time. Neither did the first exoplanet. Neither did the faint wobble that hinted at dark energy. At the moment something passes us, it usually looks small, noisy, incomplete. Meaning comes later, when patterns connect. That's why teams keep going back to old data. Not because they missed something obvious, but because context changes. New tools ask better questions. AI doesn't replace judgment here. It just exhausts the boring possibilities faster. It combs through millions of frames humans never had the time or patience to recheck. And when something survives that process, it doesn't become proof. It becomes a question mark that refuses to fade. The most interesting thing about 3I/Atlas isn't what it did, it's what it didn't do. It didn't fragment. It didn't flare unpredictably. It didn't shed mass the way fragile objects usually do after extreme heating. It didn't slow down. It didn't panic the math. It behaved consistently. That's not evidence of intelligence, but it is evidence of resilience. And resilience is rare. Now think about how small our window really is. This object spent millions, maybe billions of years drifting between stars. We observed it for weeks, measured it for days, argued about it for minutes, then it moved on. That imbalance should bother us because it means our conclusions are always provisional, always temporary, always waiting for the next data point to confirm or erase them. Which brings us to the quiet shift happening behind the scenes. Astronomy is no longer about single events. It's about surveillance of the sky as a system. Wide field surveys are coming online that don't just look at the universe, they watch it change. They notice what wasn't there yesterday. They flag motion before humans even know what to be curious about. That's the real turning point, not this object. But the fact that soon objects like this won't slip through unnoticed anymore, and when that happens, the conversation changes. Because if interstellar visitors become routine, fear fades. Mystery shrinks, patterns emerge, and whatever meaning exists won't come from one dramatic image or one leaked frame. It will come from repetition, from trajectories that rhyme, from chemistry that repeats, from timing that stops being coincidence. Until then, the most honest position is restraint. Not denial, not hype. Restraint, because the universe doesn't need our permission to be strange, and it doesn't need our fear to be vast. Right now, all we can say truthfully is this. Something passed through our neighborhood. It behaved differently than we expected. We noticed just enough to be unsettled and not enough to be certain. That's not a failure of science. That's exactly how science is supposed to feel at the edge of the unknown. And the edge is getting closer every year, not because the universe is moving toward us, but because we're finally learning how to watch. There's another layer to this that almost never gets talked about because it's not dramatic and it doesn't trend. Most space discoveries don't fail because we misunderstood the object. They fail because we misunderstood ourselves. We assume nature should behave the way we're used to. We assume randomness looks messy. We assume intention looks loud. But space doesn't care what feels intuitive to us. Plasma forms lattices. Magnetic fields fold into spirals. Dust aligns into sheets and filaments. Shock waves carve symmetry out of chaos. If you spend enough time with data from places like the outer heliosphere, you start seeing order everywhere. Not planned order, emergent order. That's why the first step in any serious investigation is boring elimination. Instrument drift, thermal noise, cosmic ray hits, compression artifacts, timing offsets between sensors, phase aliasing, geometry tricks caused by rotation and perspective. Voyager dealt with all of that daily. Its instruments were never meant to work this long. They were never calibrated for interstellar space. They were never designed for machine learning analysis decades later. So, when AI highlights a structure, the real work starts after the highlight. Engineers at places like the NASA Jet Propulsion Laboratory have spent careers learning how spacecraft lie to you. Not on purpose, but because every machine tells stories when it's pushed beyond its design limits. A voltage spike doesn't mean an encounter. A pattern doesn't mean a message. A symmetry doesn't mean a sender. It means something unusual happened in the data path. And yet, every once in a while, after you strip away the known failure modes, something still doesn't disappear. It doesn't grow stronger. It doesn't get louder. It just refuses to resolve into noise. That's the uncomfortable zone, not contact. not discovery. But persistence? Voyager 2 was passing Uranus during one of the strangest magnetic environments ever measured. Uranus doesn't behave like a normal planet. Its magnetic field is tilted, offset, and chaotic. Plasma there doesn't flow the way textbooks predict. During that flyby, Voyager recorded structures that didn't repeat cleanly and didn't fully randomize either. At the time, the explanation was simple. Extreme environment, limited sensors, move on. Which was the right call. Because science isn't about squeezing meaning out of every anomaly. It's about knowing which anomalies are worth revisiting later. And later is now, not because we found aliens, but because we finally have tools that don't get tired. AI doesn't get bored. It doesn't fill in gaps emotionally. It doesn't care what the answer should be. It flags math that doesn't fit expectations and asks humans to explain why. That's all that happened here. No announcement, no declaration, no confirmation. Just a raised eyebrow in the data. And here's the part that matters most for the listener. If this turns out to be nothing, and statistically most anomalies do, it still changes nothing about how we proceed. But if it turns out to be something, the universe didn't suddenly become strange. It always was. We just finally built ears sensitive enough to hear the quiet parts. So the question isn't, did Voyager make contact? The question is simpler and much harder to sit with. How many times have we already brushed past things we didn't know how to recognize yet? Because the universe doesn't shout when it reveals itself. Sometimes it just leaves a faint fingerprint in old data and waits to see if we're patient enough to notice. There's a reason missions like Voyager were designed the way they were. They weren't built to answer one question. They were built to stay honest when the answer wasn't clear. Voyager doesn't interpret. It doesn't speculate. It measures, timestamps, and moves on, which means everything we're talking about now is happening long after the spacecraft itself stopped caring. What we're really examining is not Voyager's experience, but our relationship with its records. Think about how much context was missing in the 1970s and 80s. No global sensor networks. No high-resolution heliospheric maps. No real-time plasma simulations. No machine learning to cross-correlate millions of data points. Back then, if something didn't scream importance, it got archived. That's not negligence. That's survival. You don't stop a multi-planet mission to chase one strange spike unless it threatens the spacecraft. So the data sat quietly. Uranus, flyby logs, voltage irregularities, plasma wave recordings, magnetometer readings. Each one alone looked explainable. Together, they didn't demand attention until now. What changed wasn't the data. What changed was our ability to connect it. When modern analysis tools re-examine Voyager's records, they don't see them as isolated measurements. They see timelines, relationships, phase alignments, repeating structures across different instruments. That's when questions start forming. Not what is it, but why does this pattern persist across systems that don't talk to each other? That's a very different question. A magnetometer glitch doesn't usually line up with a plasma wave rhythm. A voltage spike doesn't normally mirror spatial symmetry. Noise doesn't coordinate across instruments built by different teams. When that happens, engineers don't panic. They slow down. They ask whether the spacecraft itself could have created the illusion. Rotation artifacts, spin-stabilized aliasing, thermal cycling, power system oscillations. All of those have signatures. Most of them have been cataloged for decades. And many do explain parts of what Voyager saw, but not all of it. Some features survive every correction. They weaken, they blur, but they don't vanish. That doesn't make them alien. It makes them unresolved. And unresolved data is the most dangerous thing in science. Not because it proves anything, but because it tempts people to jump ahead. That's why responsible researchers refuse dramatic language. No contact, no intelligence, no message. Just this quiet, stubborn fact. Something interacted with Voyager's environment in a way we don't fully model yet. That could be plasma physics we don't understand. It could be Uranus behaving badly. It could be interstellar medium effects we've barely sampled twice. Once with Voyager 1 and once with Voyager 2. And that's the key point most people miss. We have exactly 2 data points from interstellar space. 2. Imagine trying to understand Earth's weather with 2 thermometers and calling anything strange impossible. The universe doesn't owe us clarity. What Voyager gives us instead is humility. Because every time we think we've mapped reality cleanly, space reminds us how thin that map really is. So when people hear about hidden images or strange patterns and ask, why didn't NASA tell us before? The answer is simple. There was nothing to tell. Only now do we have enough context to even ask the right questions. And those questions don't lead to fear. They lead to better science, better instruments, better models, better patience. Voyager didn't open a door. It left a breadcrumb, and the universe has been doing that since the beginning. And here's where the story gets really sharp, because it stops being about what Voyager saw and starts being about what we're willing to believe. When you run AI on old space data, people imagine a robot finding aliens. That's not what's happening. AI is more like a super annoying intern that never sleeps. It doesn't have intuition. It just keeps asking one question over and over. Is this pattern more likely than randomness? That's it. So when an AI flags something as structured, it's not saying this is a message. It's saying this looks less messy than it should. Then the humans step in and do the hard part. They try to kill the pattern. They attack it from every angle. They change the filters. They rerun with different compression assumption. They swap out enhancement methods. They shuffle time windows. They test whether the spacecraft spin could paint fake lines across data. They check if the pattern follows the instrument or follows space. Because if the pattern follows the instrument, it's probably a glitch. If it follows space, now it's a real phenomenon. That's the fork in the road. And that's where the hairs on the back of your neck start to lift. Not because it's aliens, but because real phenomena that look designed can exist in nature and still be unfamiliar enough to scare us. This is where plasma physics gets spooky. Plasma can self-organize. It can form clean boundaries. It can ring like a bell. It can create standing waves that look like deliberate pulses. Voyager 1 and Voyager 2 both heard a kind of hum in plasma wave data out near the edge of the sun's bubble. NASA scientists have talked about plasma oscillations like they're sound because it's the easiest way to explain it to humans. So if you hear rhythm out there, that's not automatically a signal. Rhythm is what physics does when a system is under tension, like a guitar string. Now stack that with the Uranus environment again, because Uranus is basically the weird kid in the solar system. Tilted magnetic field. Off-center magnetic field. A rotation axis that makes the whole magnetosphere behave like it's rolling through space sideways. Voyager 2 flew through that and still came back with readable data. That alone is a miracle of engineering. So yes, a plasmoid event near Uranus could leave behind clean geometry in the data. Plasmoids are blobs of magnetized plasma that can pinch, twist, and snap into shapes that look almost too neat. Nature can draw with a ruler when conditions are right. But here's the part you were asking about, and I'm gonna say it plainly. If I tell listeners AI found a hidden image, they will hear AI proved aliens. So the way you say it matters. You tell them the truth. AI didn't discover something in the way a human discovers a new animal. AI did reprocessing. It cleaned noise. It separated layers. It boosted faint structure the human eye would miss. It surfaced a pattern that might have been there the whole time. That's not magic. That's modern image restoration, like what scientists do with Hubble archives all the time, and even with old Arecibo legacy data when they revisit past sky surveys. So what are you letting the listener know? You're letting them know this. The new thing is not the event. The new thing is our ability to see it. That's the honest hook. And it keeps the story grounded because now, instead of screaming contact, you can frame it as a case file. A case file where the suspects are boring and the questions are sharp. Did the spacecraft create it? Did the environment create it? Did our processing create it? Or did something external create a real pattern that we haven't named yet? That last option does not automatically mean intelligence. It could mean a new kind of plasma structure, a rare boundary interaction near a planet, a weak but coherent wave mode we haven't modeled properly. Real science has plenty of we don't know yet without needing aliens. Now, there's a second layer here that's even more important for your audience. Even if the pattern is real, it could still be meaningless. Humans are pattern machines. We see faces in clouds, we see animals in constellations, we see design in random dots. So the standard is ruthless. If it's real, it has to predict something, not in a mystical way, in a measurable way. For example, if the pattern is tied to a plasma wave mode, it should show up again when conditions match. If it's tied to Uranus magnetosphere geometry, it should align with known rotation phases. If it's tied to an instrument artifact, it should appear in calibration runs. That's how you turn suspense into science. And while that's happening, you naturally weave in the credible backbone, so the algorithm tags it right and the audience trusts it. You name NASA JPL when you talk orbit and navigation. You name the Voyager plasma wave subsystem when you talk about the hum. You name the Voyager magnetometer team when you talk about field geometry. You reference the Harvard-Smithsonian Center for Astrophysics when you mention how scientists debate interstellar anomalies without turning it into a circus. You bring up the James Webb Space Telescope and Hubble spectrograph records as examples of how old data gets reinterpreted as tools improve. You mention Stanford's Ronald Bracewell concept carefully, not as proof, but as a historic idea about how probes could be designed to be quiet observers. That's how you keep it scary without becoming sloppy. Because the fear here isn't aliens are here. The fear is more grown up. The fear is that the universe can produce structures that look intentional. And we are still not good at telling the difference between intention and physics. And if that's true, then the real danger isn't what's out there. The real danger is how fast humans will jump to conclusions before the boring proof is finished. So yeah, you can say it's AI assisted, but you say it like this. AI didn't give us an answer. AI gave us a better question. And the better the question gets, the more the silence around it starts to feel heavy. And here's the part that makes this whole thing feel like a thriller, even when you stay grounded. Because once you admit AI didn't give you an answer, only a better question, you realize something else. The question is not sitting in one place. It's spread out across time, across decades, across different instruments, across different missions. And now you're basically doing detective work with a crime scene that happened in 1986, a witness that can't talk, and evidence that was recorded on a machine that was never designed to be interrogated like this. So you do what NASA people always do when they're cornered by a weird mystery. You go back to basics. You ask, what did Voyager 2 actually have on board that could even create a false pattern like this? Voyager is not a modern camera phone. It's not taking pretty photos and saving them as images the way people imagine. It's sending data, bits, streams, packets. It has sensors that turn the universe into numbers. So when someone says a hidden image was buried in noise, the first thing you ask is, what kind of noise? Is it random static from space? Is it internal electronics noise? Is it cosmic rays hitting the detector? Is it compression creating blocky patterns? Is it the spacecraft's spin smearing a signal into a shape? Because each one leaves different fingerprints. And those fingerprints are boring enough that you can test them. If it's cosmic rays, it shows up as sudden, sharp hits, not smooth symmetry. If it's compression, the pattern repeats at block boundaries. If it's the spacecraft's spin, the structure rotates or repeats with the spin period. If it's electronics, it might line up with power system cycles. So the investigators line up the timeline. They look at the moment near Uranus when the plasmoid event happened, because that environment is basically a magnetic washing machine. Then they check the power and voltage logs around the same time. If the spacecraft had a hiccup, the instruments would usually complain in some way. Tiny jumps, drops, weird offsets. Then they overlay plasma wave data, because plasma waves are like the soundtrack of the environment. If something big happens magnetically, plasma often sings. Now, if all those streams stay quiet and only the AI-enhanced imagery looks strange, it's more likely a processing trick. But if multiple streams show small, matching weirdness at the same window, the odds shift. Not to aliens, to real physics, to a real event. And once you accept it might be a real event, a new question hits you. What kind of event creates geometry? Not chaos, not fuzz, geometry. Here's where people make a mistake. They think geometry is human, but geometry is also what you get when a system has rules. Think about ice crystals, perfect shapes, not because someone carved them, but because molecules lock into patterns. Think about Saturn's rings, sharp edges, waves, gaps. Not because Saturn is trying to communicate, but because gravity and resonance are like invisible sculptors. Voyager itself proved that at Saturn. Those ring structures were so weird that early scientists were honestly shocked by how alive the system looked. If you've ever seen the way the F ring braids and twists, it looks like someone is messing with it. Nope, just physics. So a plasmoid event near Uranus creating a structured pattern is not crazy. It's just rare. And rare things feel personal. Now, this is where the story can stay scary without being fake. Because even if the explanation is natural, it still means something unsettling. It means our models are incomplete. It means there are regimes of plasma behavior out there that can imprint structure on a sensor in a way we didn't predict. And if that's true at Uranus, it could be true at the edge of the heliosphere too. Voyager 2 crossed the heliopause in 2018. That boundary is not a wall. It's more like the shoreline, where the sun's wind finally loses its grip and the interstellar medium pushes back. Voyager 1 crossed it earlier and measured a messy region. Voyager 2 crossed and saw something different, including magnetic behavior that didn't match the simplest expectations. That doesn't mean one of them is wrong. It means the boundary is not simple. It breathes. It changes with solar cycles. It shifts with the sun's activity. This is why teams at places like the Johns Hopkins Applied Physics Laboratory care so much about space weather and heliospheric dynamics. It affects spacecraft, but it also affects our ability to interpret what spacecraft hear. So when people talk about a persistent in plasma wave data, you don't frame it as a voice. You frame it as a room tone. Like when you walk into a big hall and you notice there's a low sound you can't place, not because someone is whispering, but because the building itself resonates. Space can resonate. Plasma can resonate. Magnetic fields can ring. Now, let's talk about the part that makes everyone's brain itch. The idea that the pattern looks like circuitry. This is the most dangerous moment in any story like this, because humans are trained by life to recognize man-made shapes, right angles, repeating arcs, symmetry inside symmetry. We associate that with tools. But here's the honest warning you have to keep saying, because it's true. Your brain will lie to you. If you stare at noise long enough, you will find faces. If you stare at dust long enough, you will find symbols. So the job is not to argue about how it looks. The job is to measure how unlikely it is. That's why serious people use things like Fourier analysis, autocorrelation, power spectra, and other methods that basically ask, does this structure have a signature that random noise does not? You don't need the audience to memorize the math. You just need them to respect the idea. You're not claiming contact. You're claiming there's a pattern that might be real, and the only honest way to treat it is to test it until it breaks. And if it doesn't break, you file it as an anomaly that deserves follow-up. Now let's address the elephant in the room. Why does the AI itself halt or flag hazards in these stories? In real life, models can stop for boring reasons. Confidence thresholds, error conditions, outlier detection, safety constraints in the pipeline. Someone coded it to pause when a pattern is too strong compared to the training set. That's not the AI being scared. That's the AI doing what it was told. So if you want to keep the story clean, you don't make the AI a character. You make it a tool. Like a microscope doesn't think it saw a germ. It shows you something small. Then you decide what it is. Same here. AI shows you a candidate pattern. Then you go to the next step, which is the most human step of all. You argue, you bring in different teams. You ask independent groups to reprocess the same data with different methods. That's how science prevents self-hypnosis. This is where institutions matter, not for authority vibes, but for redundancy. NASA JPL for navigation and mission history. The Voyager project scientists and engineers who know the instruments. The Space Telescope Science Institute as an example of how archives get reinterpreted carefully. The Harvard-Smithsonian Center for Astrophysics, because they're one of the hubs where these kinds of cosmic anomaly debates actually happen in public and in journals. And when you want to talk about how we search for signs of technology without losing our minds, you can mention Stanford's old Bracewell probe idea as a historical concept, not a claim. And that's the heart of the NASA style you're aiming for. Exciting story, boring standards, no screaming, No certainty, just this creeping realization. If a pattern is real and it's not an artifact, then something in the environment created structure strong enough to imprint itself on a machine we threw past a planet almost 40 years ago. And if the environment can do that, then space is not empty the way people picture it. It's active, it's textured, it's full of invisible architecture. And that idea alone is enough to make people feel small, not in a sad way, in a wake-up way. Because if the universe can leave fingerprints in our machines, then we've been living next to a library of signals we barely know how to read. And we are only now learning the alphabet. And once you reach that point, the story stops being, what did Voyager see, and becomes, how do you test a ghost? Because that's what this feels like in practice, not a monster in the dark, a shadow in the math. So the investigation moves into a phase that is almost painfully plain. You don't stare harder at the same image. You change the question. Instead of asking, what is this shape? You ask, where else should it appear if it's real? If it's an instrument artifact, it should show up in other places where the instrument was stressed. If it's Uranus-specific, it should line up with the planet's magnetic geometry and timing. If it's heliosphere-related, you should see cousins of it when Voyager is near boundary regions, like the termination shock or heliopause. So teams start pulling parallels from other missions. Cassini's magnetometer data at Saturn, Galileo's plasma environment near Jupiter, New Horizons measurements out in the Kuiper Belt, even Earth missions like THEMIS and MMS, because space plasma near Earth is a training ground for interpreting weird magnetic structures. This is where NASA-style storytelling gets good, because you can let the audience feel the method. We're not chasing aliens, we're chasing consistency. Now imagine what that looks like for Voyager 2. A spacecraft that's old enough to be a grandparent, running on power so low it's basically sipping electricity through a straw, talking to us through the deep space network, those giant dishes in California, Spain, and Australia that listen for whispers, a whisper that has traveled hours through space. So if something near Uranus left a fingerprint, it's not gonna be a clean selfie. It's gonna be faint, buried, like someone scratching a symbol into fog. And that's why AI helps, but also why AI can fool you. When you enhance faint data, you can accidentally teach noise to look like meaning. So the safest move is this. You don't trust one AI model. You throw different tools at the same raw data and see if the pattern survives. Different denoising methods, different reconstruction steps, different settings, different teams. If it's real, it should show up even when the tools disagree. If it's a trick, it will vanish the moment you change the method. That's the most honest kind of suspense because it's measurable. And here's where the audience always leans in. Because sometimes the pattern doesn't vanish. Sometimes it gets uglier, but it stays. And when that happens, the story becomes about probability, not vibes. Probability. How likely is it that a symmetrical structure emerges at the exact time you also logged a voltage irregularity? How likely is it that a plasma wave rhythm shows up near the same window? How likely is it that unrelated streams line up by accident? This is where you can name the people and places without forcing it, because this is the kind of cross-checking that labs like NASA, JPL live for. This is the kind of debate that shows up in rooms at the Harvard-Smithsonian Center for Astrophysics. This is why university groups at places like Caltech and MIT keep building better pipelines for space data, because the old way of eyeballing a graph is not enough anymore. And as the investigation tightens, another uncomfortable possibility comes into focus. Even if it's real, it might not be an object. It might be a structure in the field. That's huge, because it means Voyager didn't fly past a thing like a ship. Voyager flew through a region of space that had shape, a region of space that behaved like it had edges, like a bubble or a ring or a folded sheet. Now, if you're a regular person listening, you might think, how can empty space have edges? But space isn't empty. It's filled with solar, wind, magnetic fields, charged particles, and dust. And charged particles love to line up. They love to form boundaries. They love to organize when forces compete. So the circuit-like vibe could be nothing more than a stable plasma boundary that happens to be symmetrical. And that's still scary in a different way, because it tells you space is not just black nothing. Space is a living medium. Now let's pull in the ancient map idea carefully without turning the story into a circus. When someone says a pattern reminds them of Babylonian or Aboriginal star maps, that doesn't mean those cultures predicted Voyager. It means humans have been watching the sky forever, and humans have always drawn meaning into patterns. Sometimes those drawings are symbolic, not literal. So the honest way to use that is not as proof, but as mood, as a reminder that this feeling is old. We've always looked up and felt like the sky is staring back. And that leads to the sharpest, most adult question in the whole story. What would real contact even look like? Because people imagine a radio message, a hello, a number sequence, something obvious. But the universe might not work like that. If something advanced is out there, it might not communicate in a way we recognize as communication. It might leave signatures in physics. It might manipulate geometry. It might use low energy, subtle interactions that look like nature, unless you know what to measure. That's why the old Ronald Bracewell idea from Stanford is still discussed in the background of science conversations. Not because it's true, but because it's a clean thought experiment, a probe that sits quietly, observing, not screaming hello, a watcher that stays silent until triggered by something. Again, not proof, just a useful lens to understand why silence doesn't mean absence. Now bring it back to the present, because this is where your video needs to feel urgent without lying. Voyager 2 is still out there. It's still sending health data. It's still alive enough to tell us it's alive, but it's fragile. And every year the power drops, which means the window for clean, high quality measurements is closing. We don't get to pause time and go back for a better look. If you want the audience to feel tension, you tell them that truth. If there's anything important hiding in Voyager's archive, the opportunity is now. Not because aliens are coming, because the oldest messenger we ever launched is slowly going quiet. So the fear becomes real, but in a grounded way. Fear of losing the only witness. Fear of never being able to ask a follow-up. Fear of this mystery staying a mystery forever because the one machine that was there is fading into silence. And that leads straight into the next step of the story. If we can't send Voyager back, what do we send next? NASA has been studying ideas like an interstellar probe for years, a spacecraft designed to do what Voyager did, but with modern instruments, faster travel, and better data handling. Missions like IMAP, which is built to map the boundary of the heliosphere, help us understand the environment Voyager is traveling through. Not to find aliens, to understand the ocean we're floating in. Because whether this anomaly is a glitch, a rare plasma structure, or something we haven't named yet, the result is the same. We need better sensors, more passes, more data points. And that's the real cliffhanger. Voyager might have brushed against something we don't understand. But the only way to know is to go back with better eyes. And the clock is ticking. Not because the universe is attacking us, but because our witness is old, far away, and running out of breath. The moment it turns from a fun mystery into a serious case is when the pattern survives your best attempt to destroy it. So here's what happens in the room. Not a Hollywood room, a real one. A few engineers who know Voyager like it's their own old car. A few scientists who don't care about vibes, only graphs. And one brutal question on the table. Is this just our tools drawing shapes and noise? Or did Voyager pass through something that had real structure in space? They start with the least exciting test. The kind of test that never goes viral. They take the raw Uranus flyby data and run it through a completely different processing pipeline. Different filters, different assumptions, different settings. Then they do it again and again. Then they hand the same raw chunk to a separate group and tell them, don't talk to us, don't copy our method, just see what you see. If the shape is fake, it changes every time. If it's real, it stays stubborn. And this is where the tension gets quiet. Because the strongest version of the pattern doesn't stay. It fades. It gets less pretty. It becomes rougher, more broken, less like a clean drawing. But it doesn't disappear. It keeps showing up in the same time window. Not as a perfect picture, but as a repeating fingerprint. And when that happens, everyone in that room does the same thing. They stop talking about what it looks like, and they start talking about timing. They line up the magnetometer record. They line up the plasma wave instrument. They line up the spacecraft power and voltage logs. They line up the spacecraft orientation history. Because if Voyager rolled or twitched even slightly, it can paint false lines into real data. Then they ask the most important question: does the anomaly follow Voyager, or does it follow space? If it follows Voyager, it's a spacecraft quirk. If it follows space, now you have a real event. Now you have a place in the universe where something behaved differently than our simple models predict. And in this case, the strangest thing isn't one single sensor. It's the way the weirdness clusters. A small voltage irregularity near the same window, a change in magnetic behavior that doesn't match the surrounding minutes, a plasma rhythm that looks too steady to be random chaos. Not a message, not a voice, a rhythm. Like a room humming when the air conditioner kicks in. Like a glass vibrating when a truck passes your house. Except this room is space, and the truck is something you can't see. So at this point, the smartest people in the room are not saying contact, they're saying what kind of environment makes a machine feel like it's being touched. Because if it's natural, it's still important. Uranus is already the weirdest big planet in the solar system. Its magnetic field is tilted and offset, and the whole system behaves like a spinning top rolling sideways through the solar wind. That alone can create structures in plasma that look too clean for comfort. A plasmoid event can form boundaries, sheets, rings, knots, places where the field folds like fabric. And when charged particles hit those boundaries, instruments can record patterns that are not random, because the physics isn't random in that moment. That is the boring explanation. But boring doesn't mean harmless. Boring still means we don't fully understand what's possible out there. And then someone asks the question that changes the room again. If Voyager passed through a structured plasma region near Uranus, could Voyager also be passing through structured regions now, out beyond the heliopause? Because Voyager 2 is not just far, it's outside the sun's main protective bubble. It's in the place where interstellar space pushes back. And here's the part that hits like a cold drink. We have two witnesses to that boundary, Voyager 1 and Voyager 2. That's it, 2. So if there's weird physics out there, we are not even close to having enough examples to say what's normal. Which means an anomaly doesn't just mean mystery. It means low sample size. It means our confidence is fragile. And now the story tightens around one more detail. Communication. Everything Voyager tells us comes through the deep space network. Those giant dishes that listen so carefully they can pick up a faint whisper from a machine that launched when some people listening weren't even born yet. If you want a real climax without screaming aliens, this is it. A whisper hits Earth. It's not clean, it's not dramatic, it's just wrong enough to make the people who know Voyager sit up straighter. Because deep space signals don't get weird for no reason. Sometimes it's solar interference. Sometimes it's spacecraft aging. Sometimes it's a timing glitch. And sometimes it's the environment changing the way the signal propagates. That's the cleanest kind of fear. Not fear of monsters. Fear of not knowing what your messenger passed through. So they go back again and widen the search. They dig into more archive windows. They check other encounters. They check whether similar structures appear in other magnetospheres. They compare to what Cassini saw at Saturn, what Galileo saw at Jupiter, what modern missions use to map the heliosphere today. And the results don't hand you a neat answer. They hand you a sharper conclusion. This is not a confirmed message. This is not confirmed contact, but it is a consistent anomaly that keeps surviving kill tests. And in science, that's the moment something moves from internet myth into an actual research question. It becomes a file that won't close. Now let's be honest with the listener, because you can't sell this like a fairy tale. Even if the pattern is real, it might still be meaningless. Nature makes geometry all the time. Saturn's rings are geometry. Jupiter's storms are geometry. Magnetic fields can draw curves and spirals that look like design. Humans are the ones who panic. So the only responsible way to frame this is like a NASA reporter would. We have an old spacecraft. We have faint data. We have new tools that can highlight hidden structure. We have a set of anomalies that cluster in time. We have plausible natural explanations. We do not have proof of intelligence, but we do have something else. We have a warning. Not a warning from aliens. A warning about our confidence. A warning that our models of plasma, magnetospheres, and the boundary of the sun's influence are still incomplete. And if that's true, then this isn't really a Voyager story. It's a human story, because Voyager was never built to answer the biggest questions. Voyager was built to collect honest measurements and survive long enough for future humans to understand what those measurements meant. And we are those future humans now. So here's the final twist, and it's the quietest one. If you keep watching the sky long enough, the scary thing isn't that something is out there. The scary thing is that the universe can stay silent and still be full of forces, full of structures, full of patterns, full of things that don't need to announce themselves to be real. That's why places like NASA, JPL don't chase headlines. They chase repeatability. That's why the Harvard-Smithsonian Center for Astrophysics debates interstellar oddities with caution. That's why older data like Arecibo legacy archives keep getting revisited, because new tools can pull new meaning from old signals. That's why telescopes like Hubble and James Webb matter so much, because one good spectrum, one clean time series, can turn fear into understanding. And that's why the next chapter is not about what Voyager already saw. It's about what we build next, because Voyager is aging, power is dropping, instruments are shutting down one by one. One day, it will stop calling home. And when it does, we don't get a redo. We don't get to fly back and check. If there's anything important hiding in that long, thin whisper from deep space, the only way to find out is to listen harder, analyze better, and send a new messenger designed for the job. So no, I'm not asking you to scream aliens. I'm asking you to feel something more real than that. The universe is bigger than our categories, and Voyager 2, quietly, is still out there, still talking, still refusing to let us pretend we already understand the dark. If you want the next piece of this story, tap the next video on your screen now.